Welcome back to Discrete Math. Today we're going to talk about translating English sentences into logical statements. Here's an example. You cannot drive your car if you have poor vision unless it is corrected. Let's see if we can parse this English statement apart and write it in logical form. Let's suppose proposition A is you may drive your car. And let's let proposition B be you have poor vision. And let C be the proposition your vision is corrected. How can we translate then this original statement using these three propositions? You can see then that you may not drive your car if you have poor vision that is not corrected. And so it goes like this. If you have poor vision and your vision is not corrected, that implies you may not drive your car. Here's another example. The file cannot be copied when the drive is full. Let's let statement A be the drive is full, and B is the file may be copied. You can see then that if the drive is full, then the file may not be copied. Propositions are said to be consistent if they cannot be used to derive a contradiction. A contradiction is something of the form proposition A is true and also not A is true. A is true and A is false. Well, it can't be both at the same time. So this would be a contradiction, A and not A. In the next example, let's look at three sentences and see if we can translate them all into logical statements. The first statement is the file is stored in the queue or it is sent. The second statement is the file is not stored in the queue. And the third statement is if the file is stored in the queue, then it is sent. Let's suppose that A is the statement the file is stored in the queue, and let B be the file is sent. On the first one, either the file is stored in the queue or the file is sent. On number 2, the file is not stored in the queue. That's just not A. And on 3, it says if the file is stored in the queue, then it is sent. So if it is in the queue, that implies that the file has been sent. Here's a question. Can all 3 of these be true at the same time? Notice that if number 2 is true, then the file is not stored in the queue. If number 1 is true, either the file is in the queue or the file has been sent, but it's not in the queue, so it must be sent in order for number 1 to be true, while number 2 is true at the same time. So the file has been sent. Now, we've already assumed that A is false. It is not true that A is true. So this is a false statement here. A false statement can imply a true statement. That's true. So these 3 statements are consistent. However, if we were to add a 4th statement, statement number 4, the file has not been sent. Number 4 would translate into not B. So we have to have A or B, but if A is false and B is false, you can't have A or B be true. And so now, adding this 4th statement that the file has not been sent makes this structure inconsistent. If we eliminate this 4th one, then it will be consistent. Concerning Boolean searches, you can often search the internet using some form of browser. And there's certain things you need to be aware of. If you have some search item and you type in capital letters the word "and" some other search item, it will look for pages that have both this proposition A and proposition B. There are other Boolean search commands that you can use, all in capital letters, or proposition A or proposition B. You can have term A or term B, whatever those terms may be. You can have A not B. Look for things that include the term A but do not include the term B, which is often very useful. And you can also use A and not B. As an example, suppose we type the word new and York and museum. Suppose we're looking for a good museum to explore in New York City. This is great. It'll give us pages that have new and York and museum, but it might give us a site for the new museum in the city of York in Great Britain. So a better idea might be to use New York in parentheses and museum. So we'll search the entire phrase New York and then add to that the word museum. What would we get if we put York and museum not new? There it's looking for a museum in York, not New York. So you need to be careful about the way in which you perform these searches concerning what pages you expect to show up. In the popular Google platform, not is replaced by minus. So if you wanted to do and museum minus York, that'll leave York out of it. Look for pages that don't have the term York, but new and also museum. Let's look at a logic puzzle. Suppose that we have a game show and we have 3 doors. Door 1, door 2, and door 3, each of which bears a description. Behind one of the doors is the prize, and there's nothing behind the other 2 doors. They each have an inscription. On door 1, the inscription is, "This is empty." On door 2, it says, "This is empty." And on door 3, it says, "The prize is behind door 2. Suppose that only one of these statements is true. Where is the prize? There are a number of different possibilities to consider. One could be true and 2 could be false and 3 could be false. That's one option. Or 1 could be false and 2 could be true and 3 could be false. That's another option. Or 1 could be false and 2 could be false and 3 could be true. Let's consider this first possibility, where statement 1 is true, door 1 is empty. Statement 2 is not true, the door 2 is not empty. And statement 3 is not true. The prize is not behind door number 2. Well, if the prize is behind door number 2, then this would be a problem. So this possibility is out. On the second list here, it could be false that door number 1 conceals an empty room, in which case the prize is behind door number 1. Question number 2, statement number 2 would be true And this really is empty, whereas statement number 3 would be false. The prize is not behind door number 2 because door number 2 reveals an empty chamber. So this is a possibility, whereas if it is not true that door number 1 is empty, there's something there, there's a prize there behind door number 1, and number 2 is not true, that means you would have to have a prize behind door number 2. You can't have both, there's only one prize, so that possibility is out as well. So we deduce then the prize is behind door number 1. Here's another example known as the knights and the knaves. The rules are, for knights, they always tell the truth, and knaves always lie. You encounter two people. Person A says that person B is a knight. Person B says the two of us are of different types. I.e., one of us is a knight and the other is a knave. So who's a knight and who's a knave? There are different possibilities for A and B. They both can be knights or knaves. Knight or knave. They could both be knights. One could be a knight, A could be a knight, and B could be a knave. A could be a knave and B could be a knight, or they could both be knaves. So, which is the true possibility? Which is which? Is A a knight or a knave? Is B a knight or a knave? Well, if they're both knaves, then they're both lying. And if A lies, then B is not a knight, he's a knave. And if B is lying, then the two of us are not of different types, they're of the same type. So if they're both knaves, that's perfectly consistent with their claims both being false. You can see that if they're both knights, then when A says B is a knight, that's true, and if B is also a knight, it must be true that the two of us are of different types. But that's a contradiction. So they're not both knights. If A is a knight and B is a knave, then what A says is true, B is a knight, but wait a minute, we just said B is a knave, so that can't be the case. On the other hand, if A is a knave, then it's not true that B is a knight, which means that B has to be a knave. So that rules this possibility out too. So the only possibility is they're both knaves. I should mention that the homework adds a third category besides knights and knaves. There's knights, knaves, and spies. The spies don't always lie, but they may lie. And that's the difference between a spy and a knave. Then there's the muddy children problem. A father has two children, a boy and a girl. and he tells them that they may play in the backyard if they don't get muddy. While playing in the backyard, they both get mud smeared on their foreheads. Each child cannot see their own forehead, only the other child's forehead, and always answers truthfully. So both the boy and girl will tell the truth. Father says, at least one of you has a muddy forehead. The father asks the two children yes or no. Do you know if you have a muddy forehead? And so the father has informed them that at least one, maybe both, of the children has a muddy forehead. Initially, each child, the boy and the girl, can see that the other child has mud on their forehead, but they don't know whether or not they themselves have a muddy forehead. So if they both answer at the same time, they should both say no and no to the first question. They don't know whether they have mud on their forehead because they are sure that the other sibling has mud on their forehead, and they only know that at least one, maybe both, but at least one, has mud on their forehead. Now that both children have answered no, they both come to the conclusion that they didn't know if they had mud on their forehead because they could see mud on the forehead of the other child. So they come to the conclusion then that since both of them were unsure, then their second reply is both truthful. Yes, indeed, they must both have mud on their foreheads because they can conclude that each of them can see mud on the other's forehead. Logic circuits involve various logic gates. Each logic gate may have one or more inputs. We'll say input 1, input 2, input 3, through input k. Each of these, p sub i's, will take values between 0 and 1, just in the set 0 and 1, either 0 or 1 for each. 0 will be off, 1 will be on. We'll think of 0 as being false and 1 as being true. They may also have outputs. S1, S2, through Sj. We can have a number of different outputs for each of these logic gates. Each of these outputs may also take values in the set 0 and 1, false or true. We often break these logic circuits into simple logic circuits and mix and match these simple logic circuits to combine more complicated logic circuits. The simple one to begin with is the negation circuit. The information flow goes this way, and if you have P here, it will output the opposite, not P. So if you put in 0, it'll output 1. If you put in 1, it will output 0. So it's the negation of P. We call this an inverter. It's inverting the truth value as it goes through the inverter. We then have something called the OR gate. You'll have two inputs to an OR gate. They come to a point here and then out. So you'll have P1, P2, and it'll output P1 or P2. So if these are both 0, it'll output 0. If one of them is 1 and the other one is 0, then it will output 1. If they're both 1, it will still output 1. So this is the mathematical OR gate. We then have the AND gate. Again, two inputs. This time it's denoted by something rounded here with an arrow going out. You'll have inputs P1 and P2, and it will output P1 and P2. So if both P1 and P2 are false, it outputs false. If P1 is true and P2 is false, 1 and 0, the AND statement is still false, so it'll output 0 for false. Same thing if P1 is false and P2 is true, it still outputs false. It only outputs a true or a value of 1 if both P1 and P2 take the values of 1 or true, in which case it'll output a 1 here. Determine the output for the following logic circuit. Here we're going to have three inputs. We'll call them P, Q, and R. The second input goes to an inverter, so you'll have not Q coming out of that. The third one also goes through an inverter, and so you get not R coming out of that. We'll then take these two, we'll send these to an AND gate, which gives us P and not Q coming out of that. We'll then combine these with an OR gate, and what comes out finally is P and not Q or not R. In our next example, we want to build a logic circuit for the following logical statement: P or not R and not P or Q or not R. And so the way that we're going to do this, first on this first one, P and R, this first one has to go into an inverter, giving us not R. And then we have to put these into an OR gate. So we have P and R going in here, P, Q, and R going in over here. P has to go through an inverter to give us not P. We need Q and not R, so we still have to have an inverter for R. This is an OR, so we have an OR gate here, Q or not R. But then we need another OR gate to output not P or Q or not R. And from these two, we need an AND gate. And that will output the required output here. I find it fascinating that we can do all of this logic either symbolically using Boolean variables and also with bits. We can even construct electrical circuit diagrams that will cover these types of logical statements that we've been dealing with in this section.